Right, first I'd like to welcome everybody to the start of a new year of our monthly meetings, and I'm very pleased to be able to introduce Dr. Ros Skelton, who is the salt astronomer based at the SAAO in Cape Town. Ros did her undergraduate honours and master's degrees at UCT, and then her PhD at the Max Planck Institute in Germany, which you completed in 2010, I understand. Then she did a postdoctoral fellowship at Yale before returning to South Africa in 2013 as a postdoctoral fellow at the SAO. And in 2016, she joined the SALT team with whom she currently works. She still has connections with UCT and lectures as well as mentoring students. Her research interest area is that of galaxy formation and evolution. And we're looking forward to your very alliterative talk on cosmic crowds and crashes. Ros, thank you very much.
Thank you for having me. I hope you can all hear me. And please feel free to ask questions as we go along. If you have anything, burning questions that you'd like to have answered immediately, don't wait till the end. But I'm sure we will have some time for questions and answers at the end as well. So today I'm going to tell you a bit about my research, which really focuses on how galaxies evolve and how they are affected by the environment they're in. So whether a galaxy sort of grows up on its own, quite isolated, or whether it's crowded into a group of galaxies makes a big difference to how it evolves. And the other thing that I've been really interested in over my career so far is galaxy mergers, so crashes or collisions of galaxies, and how that affects their evolution. So those are some of the things that I'll tell you about today. Let's start by looking at what the Milky Way looks like from a place with beautiful dark skies like Sutherland. So being one of the SALT astronomers, I'm quite privileged in that I go up to Sutherland fairly often, well, at least I did before lockdown. And the night sky from there is really amazing. So I hope some of you have been able to visit places like Sutherland or Cedarburg, anyway, really dark, and have seen the Milky Way stretching over the sky above you, because I think you get quite a different perspective and you really feel like you're within a galaxy when you can see those dust clouds and some of the structure within the Milky Way above us. So I'm presuming that since you're all interested in astronomy, you're aware of what the Milky Way is, our own galaxy, and we're seeing part of our galaxy, the disk of our galaxy stretching overhead when we look up and see that Milky Way. But if we could actually escape out of our galaxy and look down on it from above, we would see something quite different. We would see something like this, which is NGC 6744. And this is a spiral galaxy. It looks quite similar to what we think the Milky Way looks like. You could see it has a bit of a bar in the middle, a sort of central bulgy structure that's slightly elongated into a bar. And then it has these spiral arms, which are where new stars are forming. So here you can see the pinkish color, which is your H-alpha emission, your hydrogen emission from new star forming regions. And most of the star formation is taking place in this disk of spiral arms around the center of the galaxy. So this is something like we expect the Milky Way to look like. If we have a look at this artist's impression of what our galaxy is made up of, you can see that disk of stars. So if you looked at it edge on, you would see a thin disk, something like 1,000 light years in height. And the extension of the disk is possibly 100,000 light years. So it's much broader than it is high. And so we have this very thin disk surrounding a bulge of stars in the middle, and that's what we think our Milky Way looks like. It's sometimes quite difficult to actually find the properties of the Milky Way because we're embedded within it. And so it's helpful to look out to other galaxies and try and compare and see what do we think our galaxy would look like if we could look at it from externally. Our sun is probably about 8 kiloparsecs from the center, so something like 25,000 light years from the center. And actually recently they've found out that the disk is probably even bigger than we expected, so maybe even extending up to 200,000 light years. It's quite difficult to tell which stars in the outskirts of the disk actually belong to the disk. And so it's actually quite difficult to tell the extent of the Milky Way, but it's something like 100,000 to 200,000 light years across. And it's made up of something like 50 billion times the mass of the sun, something like 100 billion stars in total, possibly a lot more, 400 billion stars. So there are many, many, many stars in our Milky Way. There's also the dark matter that we can't see, and a lot of gas and dust. So if you go to a place like Sutherland and look at the Milky Way, you can see that dusty structure within it. And we see that kind of dust lane structure within many spirals around us. So the gas and the gas within the galaxy is probably only about 10% of the mass of the stars, a relatively small component. But the dark matter it makes up much more of the mass. So there's actually dark matter extending throughout the disk, but also in a kind of circular halo around the galaxy. And we have things like the globular clusters found in the outskirts of the galaxy, whereas open clusters and your star-forming regions would be located within the disk. There's also a central black hole, and the black holes are found at the center of most galaxies, a supermassive black hole, and they can also have a very big impact on how the galaxy evolves. So I won't talk a lot about black holes in this talk, but we have a supermassive black hole in the center of our galaxy, and it's thought that most galaxies do. The halo of the galaxy is probably a lot older than the disk. So the oldest stars that have been found in the Milky Way are something like 12 or 13 billion years old. So there you're getting back to very early days in the formation of the universe. We think the universe is about 13.7 billion years old. And our halo started forming already somewhere around 13 billion years back. Whereas the disk, most of the stars are probably quite a lot younger, something like 8 billion years. So I mentioned already that we have this halo of dark matter around the Milky Way, around the disk. And in addition to this halo of dark matter, there are also halo stars. And some of these stars are located in kind of streams extending around the Milky Way. So this illustration just shows you another view of some of the components of the Milky Way. You can see here the Sagittarius star stream, which has been stretched and distorted. It used to be a dwarf galaxy that got into the orbit of the Milky Way and was pulled apart as it orbits. We also have the Magellanic Clouds, which I'm sure you're quite familiar with as our nearest neighbors. So these are small, relatively small dwarf galaxies that are part of our Milky Way system, or at least part of our local group of galaxies. And in the case of the large and the small Magellanic Clouds, they haven't really been distorted too much by the Milky Way itself, but some of the other galaxies have been completely pulled out of their original shape. And this image also just illustrates some of the features coming from that central black hole, the bubbles of gas that we think are blown out of a galaxy by the active galactic nucleus or black hole at the center. So we have many dwarf galaxies that we can't see with the naked eye, or even with small telescopes. The Magellanic Clouds are quite obvious from a dark place, but there are many other dwarf galaxies that have actually only recently been discovered. So if we look at some of the data coming from the Sloan Digital Sky Survey, this image here shows you the stellar distribution coming from this really large survey of stars and galaxies over most of the Northern Hemisphere. So it's called the field of streams, and you can see a couple of these stream-like structures extending all the way across the sky. What might not be so obvious is that there's actually a large stream on this end here, this kind of purplish color. That's also a stream which comes from a dwarf galaxy that's being distorted and sort of stripped as it orbits the Milky Way. There are a couple of other streams here, but there are also some point sources and some smaller sources that are a little bit hard to see in here. And I can point a few of them out. So these are new dwarf galaxies that have been discovered since the Sloan Digital Sky Survey started mapping the sky. So some of them are, for example, Bootes or Coma Berenices, some of the Leo dwarf galaxies. And so this is relatively recent discovery that there are actually probably between 30 and 60 of these tiny little dwarf galaxies around our Milky Way, as well as all of these streams, which were probably galaxies in the past that are no longer whole galaxies. So if we look at the halo of our Milky Way, we actually get a fossil record of the formation history of the galaxy. And it seems like it didn't just evolve in isolation, but it's actually changed over time. And that halo has been built up over time as these small galaxies merge into it. So when we look out a little bit further beyond the Milky Way and its dwarf galaxies, which is illustrated over here, we see another galaxy nearby called Andromeda. I'm sure all of you know Andromeda. And together, Andromeda and the Milky Way form our local group. There's a third spiral galaxy, the Triangulum, which is Messier 33. And so those are the biggest galaxies in our local group. And they all of those spirals also have all of these dwarf galaxies around them. So Andromeda probably has a similar number of tiny dwarfs. I think we've now discovered about 30, possibly even more small dwarf galaxies around Andromeda. And they would be quite difficult to spot, which is why they're being discovered really recently. So there's a new survey that came after the Sloan Digital Sky Survey called the Dark Energy Survey. And that's discovered on the order of 10 of these new dwarf galaxies a year for its first couple of years. So they're the bigger ones like Messier 110 or M32, which you can see relatively easily, but then there are a whole lot of small ones as well. And this is another sort of picture of Andromeda shown over here in the middle. And when you look at the faint structure around Andromeda, you see similar kind of stream structure as you see around the Milky Way. But you have to be able to really observe that low surface brightness material that's lying around the galaxy. So here's just a few images of M33 and M31. And here in this low surface brightness material, you see all these little dwarf galaxies popping out as well as the streams. If we zoom out even further, Andromeda and the Milky Way form our local group, but our local group is part of a larger structure. And so as you zoom out, you see more and more groups, and these groups are actually clustered together as well. So in our local universe, you could center on the local group, but then you would find other groups of galaxies like the Fornax cluster, the Virgo cluster, as you go further and further away. And it seems like most galaxies tend to prefer being in groups or in clusters. So clusters are just the largest groups we see. And there are not that many galaxies that are completely isolated. So you actually have to work quite hard to find a sample of completely isolated galaxies. There are these regions in between, known as voids, where there are very few galaxies. But galaxies like to cluster together and form these kind of filamentary structures throughout the universe. These are a couple of examples of clusters of galaxies. So here you can see the Virgo cluster, which is made up of many of these sort of smoothish looking galaxies. They're kind of yellowish or reddish in color, and they have a relatively smooth distribution. So they're quite different to the spiral galaxies like our Milky Way and Andromeda. And clusters of galaxies tend to have these types of elliptical galaxies in them, rather than spirals. So here's another cluster. You can see most of the sort of yellowish galaxies here are part of the cluster, whereas you have a couple of the bluer spiral galaxies, which might be in the foreground of the cluster. So just in case you're confused, in this image here, you've got a couple of dark spots, and those are actually just stars from our Milky Way that we're looking through, and they've just subtracted those stars from the image to see the galaxies in the background. So that's why there's some holes in that image. Okay, but if we zoom out even further, look at the universe on even larger scales beyond clusters, we find superclusters. And so superclusters are, again, groups of clusters. And so as you go out, you find larger and larger structures within the universe. So some of the superclusters near us are the Coma supercluster, with its most famous cluster, the Coma cluster within it. The Hydra supercluster, Perseus Pisces. We're part of the Virgo supercluster, and then there's Centaurus as well. And so, yeah, as I said already, these galaxies are grouped together in groups. Groups are grouped together in clusters, clusters into superclusters. And as you go out into the universe, you see this kind of filamentary structure forming. So this little plot down here just shows you the kind of sponge-like structure of the cosmic web. And we think we have quite a good idea of how this cosmic web formed. So it turns out that in the standard picture of galaxy formation, which is known as the lambda cold dark matter model, you get dark matter clumping together over time. And as it clumps together, it forms this kind of filamentary structure. So I'm going to play this video. Hopefully you can see how this is illustrating the evolution of the universe from relatively early on. This little countdown at the top here is showing you redshift, which is basically an illustration of time evolving. And so as we look at higher redshifts, we're looking further out, further back in time from the very early universe at redshift 20 or so down to redshift of 0, which is today. And you can see that in this simulation, we're looking at the dark matter particles, and the dark matter starts out relatively smooth, but there are tiny fluctuations in it in the early universe. And those tiny fluctuations cause gravity to pull together clumps of dark matter into the densest regions. So wherever you have a slightly overdense region, you're going to have a stronger force of gravity, and that's going to pull in more dark matter. And it's kind of a runaway process where you get more and more dark matter coming into that region. And so wherever dark matter is clumping together, you're also going to get gas flowing in, and that's where your galaxies are going to form. So we have a fairly good idea of how that process works. It's called hierarchical structure formation, and that's the standard picture of evolution of galaxies in the universe. And if you evolve a simulation just with dark matter particles responding to gravity, you end up with this kind of filamentary structure. So this is a different simulation, illustrious TNG. And here you can see at the centers of these filaments where the distribution is densest, or the amount of matter is most dense. That's where you're getting galaxies forming. And they tend to lie along these filaments. And in between, you have void-like structures. So just sort of a space where there are relatively few galaxies. So the dark matter is fairly well under control because it's only really responding to gravity. Whereas baryonic matter, that's all the rest of the matter that we are made of, there it gets more complicated. Just to show you one of the sort of classic comparisons over here of simulations against observations, the blue points and the purple points in these top two segments of the pie chart are showing you actual data from some of the earlier galaxy redshift surveys. And the ones in red here, the bottom two, are showing you the simulation data. And they look very, very similar. So if you simulate galaxy evolution the dark matter formation, you end up with a very similar distribution to what we actually see in the universe. But as soon as you try and add in the baryons or the gas and the stars, things do get a bit more complicated and it's a bit more difficult. Because you've got processes that are different. You've got the fluid dynamics. You've got to take into account that gas is going to cool. When it does, you'll eventually collapse the gas into stars, and you have the whole stellar evolution process, at the end of which you would have explosions like supernovae, and you've got to try and model those processes, which are taking place sometimes on very small scales, as well as the larger scale evolution of the universe as a whole, the cosmological evolution. So there's quite a wide range of scales that need to be modeled if you're going to try and simulate all of galaxy evolution, and that can be challenging. So in addition to the gas cooling and star formation taking place, the supernova explosions, you also have the black holes at the center of the galaxies, which are emitting a large amount of energy out in these jets coming from the center. So this illustration, well, this is an image of Centaurus A. You can see it's a multi-wavelength view, so over here is the optical image, showing you the sort of relatively spherical distribution of stars and the dust laying through the middle. Then you have the radio image, which is these two jets coming out from the black hole at the center. And you have the X-ray image, which is looking at the hot gas. And here they've all been combined. And this kind of multi-wavelength view is really useful for studying galaxies, because you can really see how all these different components act together. So you have this hot gas coming out from the center, a lot of energy being released from the black hole at the center. And in this case, you have relatively little ongoing star formation within the galaxy itself. And this image down here is just showing you one of the star forming regions in M17, where new stars are forming. And they also are going to be releasing a lot of UV radiation, a lot of energy, and affecting their surroundings. Then we have the mergers and the interactions taking place between galaxies. And you have the environmental processes, which we'll talk more about. So if we look back just at how do we figure out how galaxies are evolving from early times to today? Luckily, we have the advantage that as we look out, we're actually looking back in time, because the light has taken time to reach us from very distant galaxies. And so if we can see fainter and fainter galaxies further and further away, we can study the populations of galaxies at different times in the history of the universe. So this is just an illustration of how we go from the Big Bang right at the beginning through what's called the cosmic dark ages into the time when stars first started forming, about 700 million years after the Big Bang. And then as your new stars form, you end up in a period where most of the stars are forming in the history of the universe, which is called the cosmic noon. So that's sort of the peak of star formation. And in terms of redshift, that's about between redshift of 1 and 3, something like 10 billion years in look back time from today. And after that, star formation kind of slows down a little bit, and you start forming the typical galaxies that we see today. So here we are at about 13.7 billion years since the Big Bang, and the population of galaxies looks very different here to how it looked in the cosmic noon and the earliest universe. So here you can see some of the very earliest galaxies. These galaxies just marked in circles here are taken from a Hubble image. You can see they're just really little red blobs. That's what they look like with the Hubble Space Telescope. And luckily we can observe them with Hubble, but we can also observe them with the Spitzer Space Telescope and get the near infrared view. And because they're quite dusty galaxies with lots of new star formation forming right at the earliest times, they emit a lot of radiation in the infrared. And you can see here the infrared source matching what we see in the optical. And we can build up from all of these different wavelengths of light, we can build up a picture of how the light is being emitted from these galaxies and figure out how old they are, and try and get an estimate of when they formed. So these are just a few examples of what we think the earliest galaxies looked like, at least from our point of view now. And if we look at the cosmic noon, when more stars were forming, galaxies probably looked more like spirals, but probably a lot messier than the spiral galaxies we see today. So this is actually an image of one of the earliest galaxies we've seen with spiral structure. It's about 10.7 billion years in look back time from us. And yeah, before this stage, galaxies were probably more irregular, but from here on, they started forming these spiral arms. So this is an artist's impression of what the galaxy might have looked like. It's very blue and bright because there's a lot of star formation going on. But it's got this kind of spiral structure, which we see from then on towards the present day. So if we look at the distribution of galaxies from today, looking back in time, we can start to see how the populations have changed, going from relatively settled disk galaxies like we see, like the Milky Way, to more irregular, irregular structures, bluer in color because they've got more star formation back in the cosmic noon. And if we look at today's galaxies in more detail, we see quite a wide variety of galaxies. So we've already talked about the spirals and elliptical galaxies, which you see often in clusters. But then you also get some more irregular galaxies. So some examples of that would be like our Large Magellanic Cloud, you know, a lot less structured than the Milky Way, probably a lot smaller as well. And you've already seen examples of the spiral disks viewed from the side, which can give us quite a different impression of what the shape of the galaxy is. So your very elongated sort of cigar-like galaxies are probably just your spiral galaxies viewed edge on. Whereas if you look at an elliptical galaxy from any direction, it'll appear quite round. And then you have some other more exotic galaxies, which are shown here, like this penguin and his egg, which are probably caused by interactions between galaxies. So in this case, this is one of the ARP Atlas galaxies. You can see these two galaxies are interacting, and that forms a bridge between them and this tail extending out from it. And in this case, the smaller galaxy here has distorted the bigger galaxy. And so you get a lot of interesting galaxies which are probably caused by interactions. But ignoring the strange ones, we have the two main types, ellipticals and spirals. And one of my main jobs is to try and understand how do we form, or why do we have these two main classes? What causes galaxies to go from young blue star-forming galaxies, disk-like galaxies, into these old red and dead galaxies, which are rounded? So they tend to have either disk structure or a round structure. And we think that galaxies are evolving from one into the other, or from rather irregular galaxies into ellipticals and spirals. So some of the processes that are probably causing galaxies to change their shape and to stop forming stars, so they become redder and deader, some of those processes are internal to the galaxy, and other processes are external, involving other galaxies or the gas surrounding the galaxies. So galaxies also have to be aware of social distancing, and they will end up quite different if they stick around with other galaxies in a cluster or in a group compared to being in a void on their own. And most of the external processes which happen in clusters, we think of as quite violent processes. So some of the names of those processes are starvation, strangulation, stripping, cannibalism. So they all sound quite extreme. But depending on your point of view, they can also grow the galaxy and cause the galaxy to double in mass if it interacts with another galaxy, for example. And so that could be a good thing if you're a galaxy. If we look at clusters in a little bit more detail, you see there are many, many galaxies clustered together, grouped together. But in between those galaxies, there's also a lot of hot gas. And that gas we only see if we look in the X-ray, for example. So that gas is about 1 million degrees. And the galaxies within the cluster are embedded in this hot gas. And that hot gas can also have very strong effects on the galaxy. So some of the processes taking place, it's a sweet illustration here, some of the processes depend on how the galaxy interacts with that hot gas. For example, ram pressure stripping. You have a galaxy that's orbiting around the cluster and falling into the cluster. As it falls in, its gas, the cold gas within the disk of the galaxy is being stripped out by the hot gas of the cluster. And so that's called ram pressure stripping. And then you have a lot of other processes which depend on having multiple galaxies around it. So you get galaxy harassment, which could just distort the shape of the galaxy, or you get actual mergers of galaxies taking place. And I'll talk quite a bit more about mergers because that's one of the things I've been working on a lot. But here are a few examples of these stripping processes which are taking place in clusters. So here you can see the gray image in the background is the optical image. And the white is a radio image or the radio contours. So this is showing you where the neutral gas in the galaxy is. Most of the hydrogen in the galaxy shows up in the radio observations. And most of the stars are shown in the optical. So in some cases, these old cluster galaxies in Virgo, in some cases you can see there's a very long tail of neutral hydrogen beyond the disk of the galaxy. It's being pulled out as the galaxy sort of falls into the cluster. So that's the case for both of these top two galaxies. And in other cases, in this case here, the galaxy is sort of, as it falls into the cluster, its gas is being pulled out behind it. And so you end up with gas beyond the disk here being stripped. And some of these galaxies are called jellyfish galaxies because they form these tails of gas behind them. In other cases, you find that there's actually very little gas left. So a normal galaxy that is evolving in isolation will probably have a lot of gas in it. And the gas disk will extend well beyond the disk of stars. But in this case, for example, the gas disk is now really small compared to the stars. And there's very little gas left because it's been stripped away. So looking at galaxies in the optical and the radio at the same time is really, really useful. And this is something that we're going to be doing a lot with MeerKAT, the MeerKAT radio telescope as it comes online. Well, it has actually already started collecting a lot of lovely data. And so you'll start to see more and more results from MeerKAT come out. Here's a little simulation showing why we think galaxy interactions might be important for forming those red and dead elliptical galaxies. So if you start off with two disk galaxies of similar mass and they interact, if you look at them at some stage in the middle of that merger process, you'll find these bridges and tails of stars being pulled out of the galaxy. So on the right here, you're seeing the distribution of stars in a simulation. On the left, you're seeing the distribution of gas, and we're just looking at it from 2 points of view. So in the top, we're looking at it face on, and the bottom two panels, we're looking at it edge on. And you can see here, you can see the gas sort of being pulled and distorted as the two galaxies have merged together. The stars, which started out as nice disks, are now all sort of scrambled, and they form something much closer to an elliptical galaxy. So a much rounder distribution, random stellar orbits. And you also see these kind of streams in the outskirts, which would get fainter and fainter over time. And you'd end up with a nice ball of galaxies like an elliptical. So that's what we think happens with a major merger. In the case of a minor merger, you might just distort the disk or you might have you know, an elliptical galaxy just absorbing another small galaxy, and it wouldn't have a lot of impact on the structure of the galaxy. Cannibalism is where we think the galaxies at the centers of clusters are absorbing these small galaxies around them, cannibalizing them, and they grow in mass because of that. And then harassment is just where you get all of these tidal distortions from many galaxies nearby without them actually merging together. So if we look at interactions at different stages, we would start out with pairs of galaxies that are clearly distinguishable as separate galaxies. And as they come together, their shape would be distorted by the tidal effects, and they might eventually form something that looks more like an elliptical galaxy. And that process has been an idea for how elliptical galaxies formed since the 70s. But we've learned a lot since then, and we've been able to simulate these processes in a lot more detail since then. This is another recent simulation showing you the stars in the galaxies on the left and the gas on the right. And you can see how a group of galaxies might start out with multiple galaxies in the same neighborhood and eventually merge together to form a really massive elliptical galaxy. So you can see as they merge, you get some of these shock waves in the gas. The smaller galaxies will eventually orbit into this massive galaxy at the center and form a massive elliptical. So that's what we think is taking place at the centers of groups and clusters, where you end up with a really massive elliptical. That's what it looks like today, but in the past, it might have actually been made up of many, many small galaxies merging together. There's still a lot of open questions about all of these processes and mergers in particular. So we'd like to know whether all ellipticals form by merging, or could they form just by gas collapsing directly into a spherical distribution? We'd like to know when mergers take place, how often does it happen, and is that changing as we look back throughout the universe's history? And does it differ depending on the environment a galaxy is in? So we think it is going to be different. In the denser regions, you're probably going to have more mergers, but perhaps in clusters it's actually less common than you would think, because the galaxies are all moving relatively fast relative to each other, and mergers might actually be quite difficult there. And then we'd like to understand more about what impact these mergers actually have on the galaxies. So to study mergers in more detail, we can look for close pairs of galaxies that we think are going to merge in the future, or we can look for distorted systems that we think have already undergone a merger. And we can use those to count the numbers of mergers we think are taking place in different populations as we look back in time. To do this, we need good images of galaxies. We need redshift estimates. So in order to measure the distance to these galaxies and to measure, for example, whether the galaxies in a close pair are actually at the same distance from us, or if one is in the foreground and one is the background, and they're actually unlikely to merge together. So that we get from spectroscopy, from looking at the spectrum of a galaxy and trying to identify features that would tell us if the two galaxies are at the same distance from us. And then we need a lot of the other properties of the galaxies. We need estimates of their masses and their star formation rates, for example, which also they can come from spectroscopy, or it can come from photographs of galaxies in a whole lot of different filters, and combining all the different color information from galaxies, you can build up that picture of the whole property, the characteristics of the galaxy, how many stars it's forming in a given time, and how much mass it already has. And we want to look at galaxies in pairs and distorted galaxies to understand galaxy mergers in different environments. So one of the projects that I've been working on recently to look at mergers looks at cluster galaxies. And to do this, we're using the beautiful data from the Hubble Space Telescope. It's called the Hubble Frontier Fields Project, which looked at 6 clusters of galaxies. So here's just one example of them. This is the Abel cluster 370. You can see most of these sort of yellowish elliptical galaxies are the members of the cluster. But there are also these very extended arcs of bluer light here. And those are distant galaxies behind the cluster that have had their light distorted by the mass of the cluster as it makes its way to us. And so those are what we call lensed galaxies. And the galaxy cluster is acting like a giant lens, bending the light from distant galaxies behind it, around it, and magnifying them in the process and stretching them out into those arcs. And so these clusters have been chosen for this very, very deep Hubble Space Telescope program because of their lensing properties, because they're actually magnifying the very distant galaxies behind them. So there are many studies looking at these very distant galaxies, some of the earliest galaxies in the universe that have been magnified by these clusters. But in my work, I'm looking at the cluster itself, so the galaxies within the cluster, and trying to look for mergers of galaxies in those clusters. So one of the 6 clusters that we started with was called MAX J0717. It's a very interesting cluster. It's actually quite elongated in this direction. So I'll show you another image in a few minutes, showing you this kind of filamentary structure of the cluster. And it's actually made up of a few subclusters or groups that are merging together. So it's not a relaxed cluster. It hasn't yet reached its sort of rounded shape, but it's clumpy, and it's got a lot of galaxies sort of still coming into the cluster. This cluster is at about 5 billion years in look back time from us. So this is redshift of a half. And we picked it because we want to see how the merger fraction in clusters is evolving. So we've got examples of clusters nearby, but we want to extend out further and further away and try and look at the merger fraction in distant clusters to see how that merger fraction is evolving. So here we searched for the members of the cluster to distinguish between the foreground, the cluster itself, and all of the galaxies in the background. We found about 380 cluster members. And then we looked for which of those galaxies in the cluster are undergoing mergers or interacting. This is just showing you the X-ray gas in blue in the cluster and the radio emission. So coming from the jets caused by black holes in some of these galaxies, the radio emission observed with the very large array in pink or red here. So you can see that there's a lot going on in this cluster. So as I mentioned already, it's got these subclumps, and it's a very disturbed cluster. So it doesn't have a nice spherical distribution of gas. It's also got clumpy gas going on, but it's a very, very interesting cluster. And within this cluster, we searched for pairs, and we searched for distorted galaxies. So this is work that one of my students, Munira Hussain, did. And here are a few examples of the galaxies that we found interacting within the cluster. So some of them, you can see they're still distinguishable as disk galaxies. They haven't been very distorted yet, but there's sort of stars between them, so signifying that they're actually very close together and will merge in future. In others, you find these tidal features, and they're quite distorted. And then you get a few with very tiny neighbors. So in this case, you might actually have multiple mergers going on. This small galaxy merging with this one, which will merge with this big central. So you have a lot of mergers going on in this galaxy, in this cluster. But in the end, it looks like only about 7% of the cluster galaxies are involved in mergers. And that fraction of mergers depends on the masses of the galaxies we're looking at. So it turns out that the more massive galaxies in the cluster are more likely to be involved in mergers, and they have a merger fraction of something like 17%. So perhaps a fifth of the galaxies, the massive galaxies in the cluster, are interacting with another galaxy. And these merger fractions that we're seeing in this cluster at redshift of a half are quite a lot higher than what we see in the local universe. So it seems like there is some evolution in that merger fraction. Once we've identified the mergers, we can start to look at their properties in more detail. So this is an image of the cluster again, and all of the cluster members are marked with tiny green crosses. You probably can't see a lot of detail, but you can see that the cluster members extend across this whole image. And the mergers we've identified are shown with the slightly bigger symbols. So here, the triangles are galaxies that are visually disturbed. And they found also throughout the cluster, some of them in the outskirts, some of them in these subgroups, which are merging together. And if we look at the close pairs of galaxies, so these are the galaxies that haven't yet merged, but we think will merge, we find that they're more centrally concentrated. So they also seem to be associated with these subgroups within the cluster. And they're not really found in the outskirts. So we have to try and understand why that is. Perhaps the galaxies that are visually disturbed already had their merger quite a long time before. And so they might be falling into the cluster already coming with this disturbed structure. And then as galaxies sort of settle towards the middle of the cluster, they might undergo further mergers, and we're seeing those as the close pairs. So this is another image of the cluster, just showing you the contours here are showing you where most of the mass is within the cluster. You have these groups that are merging together to form the cluster. This is all identified from the lensing signature. So the mass distribution of the cluster is inferred from either from the X-ray gas or from the lensed galaxies in the background that we're seeing through the cluster. And here again are just where the mergers are. And you can see they're mostly lying along this kind of filamentary structure that's forming the cluster, but many of them are associated with these little groups. So here I'm showing you group C and group D. And you can see many of these close pairs of galaxies are found within those groups. And then this is group B over here. Again, many pairs of galaxies. And group A at the top, again, has a few close pairs. So these close pairs of galaxies seem to be found where the galaxy distribution is densest, whereas the visually disturbed galaxies are lying throughout the cluster. And so from here, we can compare our merger fraction to other measurements of the merger fraction. Don't worry too much about the details of this, but here we're looking at the fraction of mergers in a cluster as a function of look back time or redshift. And you can see overall trend is actually that the merger fraction increases as you look back in time. There are some other studies which are ending up with a very high merger fraction in the local universe, but those merger fractions are probably determined in quite a different way to ours. So our points are these filled points over here. And the overall trend is that the merger fraction increases as we look back in time. So from here, we want to extend the study to the other 5 clusters in the Hubble Frontier Fields program. Those are all sort of lying here in this middle part of the diagram, quite far from us, so not very local universe, but not the very high redshift distant universe either. So filling in this middle part of the evolution picture. And we want to start characterizing the properties of these merging galaxies better. So to do this, we can use MeerKAT, we can use SALT, and the combination of the two is very powerful because we can look at both the neutral gas in the galaxies, the hydrogen coming from MeerKAT, or we can look at, or we can improve our distance estimates to identify close pairs and look at the properties of the galaxies in much more detail using spectroscopy from SALT. There are a few other projects that are, actually a lot of other projects that are ongoing. I'm not going to talk about them, but I just thought I would mention 2 two of the ones that are keeping me occupied at the moment. One of them is looking at ultra diffuse galaxies. So these are very, very faint, low surface brightness galaxies that are found in clusters as well. Here you can see an ultra diffuse galaxy compared to something like Andromeda or other typical galaxies. And you can see it's actually quite large in extent. So this is to scale. But it's very, very faint. And this is why they're called ultra diffuse. And they were sort of surprisingly discovered in the Coma cluster in about 2015. It was found that there are a lot more of these ultra diffuse galaxies than were known before. And that's a relatively nearby, well-studied cluster. So it came as a surprise that this whole population of galaxies exists, and we don't really understand how they formed or why they survive in clusters. So the idea is that, as I've mentioned, the cluster is a very turbulent environment. In some cases, there are a lot of other galaxies that could distort and pull galaxies apart if they don't have much matter holding them together. And so it's a bit of a mystery why these ultra diffuse galaxies can actually stay together as a galaxy and not be distorted as they orbit in a cluster. So that's one of the other projects that I'm working on at the moment. And then we have another project which is looking at the filamentary structure of the cosmic web. So in that project, we want to understand where the filaments are a particularly important environment for galaxy evolution. So not the clusters, which are found often at the intersection of multiple filaments where it's really dense, but the filament itself. Does that have an impact on the types of galaxies that we see in those regions? So those are two of the main other projects that I'm working on. And for all of these projects, SALT and the Meerkat radio array and many of the other facilities that we have access to here in South Africa are going to be very important. So luckily for me, as one of the SALT astronomers, I know what SALT is really good for, and I can sort of put together projects that try and make really good use of SALT. But I'm also involved in quite a lot of Meerkat projects. So Meerkat is really producing some exciting first results, and we have a long way ahead of us with Meerkat and with the follow-up to Meerkat, which is going to be the square kilometer array, which they're starting to construct already later this year. So it's a very exciting time to be an astronomer in South Africa with these wonderful facilities. And in addition to this, we have all of our steerable so small telescopes that can look in any direction. We have a number of surveys coming up that are really going to map the whole sky and map it very quickly. So you get repeat observations of the sky every night. And from that, you'd be able to identify all sorts of variable objects. And so there's a lot of exciting work happening at the moment. I think I'll leave it there and take any questions.
Thank you very much, Ros. Does anyone have any questions?
Can I ask one?
Yes, certainly, Derek.
Yeah, obviously dark matter is a big factor in all of the galaxy maneuverings and so on. But dark energy, does that ever considered, or is it just a sort of overall same effect everywhere? Is it not considered at all?
We don't consider it much when it comes to galaxy evolution. It's affecting the overall expansion of the universe and how the universe is evolving. But when somehow it doesn't impact very much on galaxy scales. It's more the matter within the galaxy and within the structures around galaxies that's having a big impact. So it matters for the overall model of the universe, what goes into our simulations of galaxy formation, but it doesn't have a big impact on the galaxies themselves.
Ros, I want to ask, sorry.
Johan Retief, can I ask a question, please?
Yes, please do, Johan.
Dr. Skelton, just looking at the picture of Meerkat, Can I ask you a meerkat question? Basically, I want to know, does Elon Musk's Starlink satellite system in any way interfere with meerkat?
It does, unfortunately. So these, having many satellites in the sky is going to definitely create more radio interference. And there are already, quite a lot of the radio sky is already blocked by, radio, sort of man-made radio frequencies. And that's unfortunately only going to get worse. So it does have a big impact on the radio, as well as the optical, because you get these streaks of light through your optical images where you have satellites passing overhead. And that's going to be particularly important when you're doing large surveys of the sky. And you have these streaks from satellites actually ruining many of your images. But there are ways which they're trying to mitigate this. So I think certain frequency bands, which are important for radio astronomy, are being sort of blocked off and tried to sort of make that safe and keep it pristine. And yeah, hopefully it won't get a lot worse over time. But it's definitely something that has to be discussed with the companies putting up satellites, and they have to try and work out how to improve it for everyone.
Thank you very much.
Can I make a comment on that as well?
Mm.
I'm on a WhatsApp group with the director of SKA, and somebody asked him that question. And I think he answered that the SKA engineers are actually working directly with the link, what is it called, SpaceX link, whatever it is, with their engineers to include some sort of a software to control their satellites so that the interference is minimized.
Yeah.
Thank you.
Yeah, and they're doing things like trying to paint this, trying to make the satellites a darker color so that they reflect less sunlight, putting up shields to also prevent reflection. So they are working with astronomers, I think, both in the radio and in the optical wavelengths to try and mitigate this. But it's a concern for astronomers still.
Ros, can I ask how long ago the link was made of that there's an association between dark matter and galaxy evolution?
I think already in about probably the 80s or 90s, people were already starting to realize that dark matter is going to control a lot of, cause a lot of the matter to clump together, and that forms these filamentary structures. So I think already in about the 70s and 80s, actually, they were already starting to realize that there's dark matter that's having an impact.
Right.
And soon after it was realized that from the motion of stars in the galaxy that there must be matter out there beyond what we can see, they started to look at the effects of this dark matter. So it's been part of simulations of galaxy formation since the simulations really got going. But obviously the simulations have improved so much over time. And initially you could only really simulate the gravitational processes. So you could treat either stars or dark matter particles just as particles experiencing these forces of gravity towards each other. But more recently, they've started incorporating all the baryonic effects, the gas effects, and being able to do that all together to get a sort of much more complete view of galaxy formation.
Right, so it actually goes back probably almost a third of a century then, the link.
Yeah.
The awareness of the link. Yeah. And then what about the sort of, what I understand is a sort of growing understanding of the nature of the cosmic web. Is that influencing simulations, etc.?
The cosmic web?
Yeah, because I understand that, there are people still trying to study it and understand it and, get a grip on the details.
Yeah.
Does that influence your simulations?
Yes, so I think the idea that there is this kind of filamentary structure that's already been known since those early redshift surveys, which were late 80s and 90s, and the simulations sort of coming in from probably the 90s. But the details of how filaments impact on galaxy evolution, for example, that's something we're still learning about now and trying to look at from the observational side. I think we have the tools like Meerkat, for example, to look at the gas in galaxies. And we need to look at the gas to understand where the fuel for star formation is coming from. And so we can start to study that kind of filamentary structure in multiple wavelengths, or looking at the gas as well as the stars, and learning more about the filamentary structure from the observational side. And then we'll be able to compare with simulations and use that to improve the models. So it's a kind of cyclical relationship between modeling and observations, where you're always comparing, trying to figure out what we've left out of the models, what physical processes are we not really taking into account, and also trying to infer from the models what's going on. So yeah, they inform each other.
Mm-hmm. So it sounds like you're never going to actually be bored. You're going to have plenty to do.
Yeah.
as all the sort of,
plenty going on.
Yeah, there's a lot going on, but also the sort of computer capacity and the advances in technology, obviously very helpful to you.
Yes. Yeah, and the simulations have come a long way. So we advancing on both the observational side and the simulation side, and it's very exciting.
Yeah, it sounds great. Does anyone else have any questions for Ros?
Yes, I was going to ask about the globular clusters. When we were, going back in your lecture, we're going through the cosmos, so to speak. There's an awful lot of globular clusters which are made up of, which I assume are made up of stars about the size of our sun, all getting together. There must be a hell of a lot, there must be an awful lot of mass in these stars. Do they have any relevance over the shaping of the cosmos they happen to be in?
I think they're going to have a relatively small scale impact. So you have these, groups of stars clustered together in a very tight globular cluster, and they're all bound together by gravity. But I think they're going to have a relatively small impact on their surroundings. So you might have a lot of these clusters within the halo of a galaxy like our Milky Way, but you could think of them as other little particles orbiting around the Milky Way. They, in a way, they could be thought of quite similar to these dwarf galaxies, but they're probably smaller and more compact, and they're not likely to be as easily stripped as they orbit the Milky Way. But they're unlikely to have a big impact on things further away from them. I'm not sure if that answers your question.
Thank you.
It's Marcus. Can you hear me?
Yes.
Yes.
The black holes in the galaxy, does that affect mergers, or?
Yes. So we think the black hole, well, the active galactic nucleus can be triggered by an interaction. So as your galaxies merge, particularly if they have a lot of gas in them, that gas can get funneled towards the center of the merger remnant, where the black hole growing at the center has more access to that gas. And so the black hole can then start accreting more of the gas, which is going to make it more active. And then you might end up with these jets coming out and a very bright active galactic nucleus. So we think that is actually part of the cycle of an interaction, that you might get more activity coming from the central black hole, and you might get more star formation as that gas settles in the center of merging galaxies.
Thank you.
Yeah, we actually, people have been looking for pairs of black holes, because if each galaxy has a black hole, as they merge, the black hole at the center of each of them is going to also, they're going to spiral together and eventually merge as well. And you might end up growing the black hole in that way. So people have been looking for pairs of black holes that are very close together within disturbed galaxies, or even looking for triple black holes. It's quite hard to find these things, but they have found a few candidates now for dual black holes.
Ros, when we talk about black holes, makes me think about gravitational waves. Does any of the new work and the new findings of gravitational waves have any effect on your work?
At the moment, most of the gravitational wave detections have been from merging stars or neutron stars, or stellar mass black holes. But we should also be able to detect the gravitational waves coming from these merging supermassive black holes. So I think definitely in future, it'll be something interesting to look out for. Yeah, I think we haven't quite got to that stage yet, but hopefully in future we'll learn about the merging black holes and galaxies from the gravitational waves.
Yeah. Are there any other questions from anyone?
Can I ask one slightly off topic again? The odd radio circles discovered by the Australian version of the SKA a few weeks ago. Do you know anything about that? Has anybody come up with any theories? Because it doesn't fit any current sort of whatever it might be. Do you know about anything about it?
No, I actually don't. I'll have to go and look that one up. So you say radio circles. Do you know within our galaxy or where these are found?
No, they're sort of beyond the galaxies. I'll just read a paragraph here. The astronomers have been unable to explain what is causing the rings of radio emissions, which they've dubbed odd radio circles or AUX. However, other telescopes have confirmed they are real and not the result of a software error. And even more bizarrely, the ghostly blobs don't appear in images taken with optical telescopes. So Professor Ray Norris wrote of the discovery, Western Sydney University. None of us have seen anything like it before, and we have no idea what it is.
Okay, that sounds very interesting. I'll have to go and look at that. Yeah, I'm not sure.
Okay, if nobody else has any questions, Ros, I'd like to thank you very much indeed for a fascinating presentation. It's always great hearing people talking about their work, what they're immersed in, and we get the sort of up-to-date news on what's happening. So I really appreciate your time, and we send you all the best for the next few months.
Thank you very much. And yeah, hopefully I'll be able to meet some of you in person one day.
That would be nice. That would be lovely, yeah. Thanks again very much.
Okay, thank you. Bye, everyone.
Ros, just one more thing, just to confirm, to be able to share the video that I recorded with some of the people. The easiest for me is to upload it to YouTube and then send them the link. Is that okay?
Yeah, that's great, Derek. Thank you.
Yeah, that's. Could you just send me the link as well?
Yeah, sure. Okay, I'll do that.
Thank you. Okay, good night, everyone.
Night. Thank you very much.
Good night. Thanks for a great talk.
Bye.
Thank you. And thank you very much, Derek.